So good morning, everybody. It's my pleasure to introduce to you Ralph Grishman from New York University. And basically, if I understand what it's about, we will be speaking about information extraction. Am I right?
Yes.
Okay. So, please, you have the floor.
Okay, thank you. Okay, so I will be talking about some effort which has been underway at NYU in building a customizable relation extractor. Okay, so starting very basics, information extraction involves converting selected types of information in natural language text to structured form so that we can search this information and reason about this information. So as one aspect of information extraction, we will focus in particular on the task of relation extraction. Relation extraction involves binary relations, generally between mentions of two entities appearing in the same sentence. So if we get the sentence, Fred, a native of Brno and father of Elsa, we could imagine extracting two relations from that phrase. One between Fred and Brno, and one between Fred and Elsa. So I've been doing information extraction for a long time, probably longer than I'd be willing to admit. And when I started doing it, I imagined, in a few years, everybody will have an information extraction engine and be using it, and I'll have to work on something else. Well, 40 some odd years later, that hasn't come to pass. Certainly there are information extraction engines, but it's not the case that every place we'd imagine wanting to use information extraction, a system has been built and it's in place and running smoothly. One of the bottlenecks which keeps information extraction from being so widely used has to do with identifying all the ways in which one particular relation may be expressed. So a particular semantic relation can be expressed in many different ways. Fred is an alumnus of NYU. Fred graduated from NYU. Fred received his degree from NYU. So somebody comes and wants to extract that relation, you have to figure out all the ways that relation may be expressed. And identifying these linguistic variants for a new relation is a difficult task. At least we tell the customers it's a difficult task, so they'll pay us well for it. And the difficulty of this task is one of the major factors limiting the use of information extraction systems. So the practical challenge we see is producing a tool for customizing a relation extractor to a new relation so we can get reasonable performance, meaning basically finding most of the correct instances of the relation. But at the same time, which can be used by a subject matter expert with limited training in NLP or information extraction. Basically, can we get a non-expert to build systems for us? So this is an outline of the issues I'm going to go through in the next hour or so in order to try to answer that question. So first, a few words about the test corpus, which we'll be using several times in the presentation to evaluate our system. The corpus we were using is the ACE corpus, which was annotated by the Linguistic Data Consortium for the ACE research program about 10 years ago. They annotated several hundred documents each year with 5 or 6 major types of relations. These are relatively broad relations, such as this is org-af relation, which represents any affiliation of a person with an organization, an employer, employee, member, and so forth. The LDC did a full manual annotation of all the entities and relations, including some which was even dual annotated and adjudicated, so that you'd get high quality annotation. And as I said before, this is the primary evaluation corpus for relation extraction. There are not many groups which can afford to annotate several hundred news articles completely for all the entities and relations in order to do an evaluation. Okay, so we'll start with the most basic question. What basic approach should we use to building extractors? Somebody comes to us and says, we want to build a relation extractor connecting cities to weather or something. So one approach is to say you got to write it all yourself. Just a large number of hand-coded rules. And hand-coding information extraction remains the primary approach for commercial and operational IE systems. It's maximally flexible. Anything you can write as a rule, you can stick into your IE system. And it's relatively transparent. By transparent, I mean you can understand what's happening with the extraction engine. There's not a lot happening, so to speak, under the hood. The trouble is hand-coded rules are not suitable by itself for our goals of having lots of people build extraction engines. Building a good set of rules requires time and experience to produce a good performance system, starting with a manual corpus analysis. If I want to extract a particular relation, such as org-af, or place of birth, or place of death, I really can't just make things up from scratch. In order to do a good job, I should read lots of articles containing this information and see the different ways in which it's expressed. And that's better suited to system developers. You go to a customer, they're not willing to read 100 or 200 articles and sit there with a highlighter and mark things up. So it may seem a natural thing for an NLP person to do, but it's not a natural thing for most of the people who want to use IE systems. Okay, so one possibility is doing hand-coded rules. Because rule writing requires a certain degree of art, an alternative approach is to do supervised training. Train a classifier using a fully annotated corpus, such as the ACE corpus, marked with all the instances of the relations of interest. The advantage of this approach is it needs less expertise in writing rules by hand. And if you have enough money to hire multiple annotators, you can speed things up by having them all do it in parallel. Or getting all your graduate students to do the annotation by saying they won't graduate unless they've done it. Okay. The disadvantage is, unless you have lots of cheap graduate students, it's a quite expensive procedure to do a lot of annotation. So not good if a customer comes in the door and says, I want a system tomorrow. Okay, so at one end is fully supervised training. At the other end of the spectrum is unsupervised training. So that's sort of an ideal we've been working with for a long time. To learn the relation and event paraphrases automatically from a corpus, so that you can recognize that graduated from NYU and is an alumnus of NYU mean the same thing without having to enter any information oneself. Just suck it all in from the web, digest it, and figure this out. So the basic approach is a distributional analysis which determines the similarity metric. If you notice that Fred graduated from NYU and Fred is an alumnus of NYU, appear with the same pair of arguments, and you gather that information over a lot of instances, you can get these sort of paraphrase relations. And there's certainly been quite a bit of work on that, but there are multiple obstacles to getting this to work well. I won't go through this in detail at the moment, but the performance is not very good yet in learning this fully automatically. And you have the additional problem that it may not capture the relations of interest to the user. If there's several ways of chopping the world up into different relations, you may get a quite different division of facts, of relationships, from what you're looking for as a customer. Okay, so if we don't have a clear match between what unsupervised is going to produce and what we want, we can have some compromise, which is a semi-supervised training, in which I annotate a small number of examples, and we use that as a seed for building a larger set. So starting from the seed examples, the system incrementally builds clusters around the seeds using the same sort of similarity measure. And this works fairly well for a while and then sort of falls apart. And part of the problem is not knowing when to stop building these clusters. That's referred to as the problems of semantic drift and spread. So it produces usable but not great extraction systems. And that's also true of a recent variant called distance supervision, which for the past couple of years was a hot thing to include in a paper you were submitting to an NLP conference. I think that's probably near the end, and the hot thing for next year is going to be neural network matching procedures. Anything with neural networks next year is going to be accepted by a conference. It's going to be good for 2 or 3 years till they figure out the next hot thing. In semi-supervised learning, you start with a seed, and then the cluster is grown basically automatically by adding similar items. Active learning also starts with a labeled seed and a large unlabeled corpus, and the system selects examples to add, but then they're passed by the user for annotation. We don't take them automatically. We ask the user whether this is an acceptable example of a particular relation. And we try to select these examples in order to get maximal information from each question we ask the user. So we look at issues like uncertainty or disagreement among classifiers to select good examples. And in particular, the bootstrapping, the semi-supervised methods, can be used to guide the active learning process. In the active learning process, the user or the customer is sort of passive. You come up to the customer and say, here's a sentence, yes or no. And the customer goes, yes or no. And then comes up the next example. We'd like to have the customer feel in control, even if they're not in control. So at each step, we're going to give a choice, basically. The system can let the user can let the system control the learning process. So the user just goes yes or no. Or the user can take the initiative and say, I have a better example for you. This requires a fairly transparent model, meaning the user has to understand what's being learned at any given point. But with that possibility, mixed initiative active learning seems the most attractive approach. Is it going to rain through at some point? Shall I stand here? Okay, so we want to use this active learning approach to learn a new relation. What features of the relation are we going to capture? We're going to learn with this active learner. So the most straightforward approach is to just use the words between the two arguments as the feature to be learned. The trouble with just using a word sequence is too much irrelevant variation has to be included. Fred is a 2012 graduate of NYU. Fred is a recent graduate of NYU. Fred is a proud graduate of NYU. All would be different features. By building a dependency tree for the sentence, and just looking at the path in the dependency tree between Fred and NYU, up is graduate NYU. For all these different variant sentences, we'll have a single dependency path. Technically shown here. Fred, subject, inverse, is, direct object, graduate of. Basically, point is one feature covers a whole bunch of examples. So it covers recent, covers proud. But it turns out it's not sufficient to make some distinctions. There are a lot of relations which are which are expressed in terms of very few words. So if we had Zabrisky's Mazel Tov, where the only connection is this apostrophe S, this could mean a whole bunch of different relations, depending on what you know about Zabrisky and Mazel Tov. It could represent the book Mazel Tov by Alexander Zabrisky, someone named Mazel Tov from the town of Zabrisky, or a Mazel Tov made by the Zabrisky factory. So we need a little more information than the dependency path. And it turns out the path plus the semantic types of arguments produces pretty good feature for selecting relations versus non-relations. I felt obliged to stick in some numbers in order to have an acceptable talk. So we put a few numbers in here. These represent the performance of a trained relation extractor using just the words, the dependency paths, or the paths plus the types of the arguments, meaning is the argument a book or a place or a person, something like that. And we can see dramatic differences. Using just the words, we get an F measure of 10%. Nobody's going to pay you for 10% doing anything. Even if you come and say the state of the art is 7%, nobody's going to pay you for 10%. You have to find some task which you can do at 50% in order to get paid. So just the dependency path produces 38%. The dependency path plus type produces an F measure of 50%. So quite good considering it's a very simple approach. Okay, so this is basically going to be the feature we want to learn. We want to learn the paths, we want to learn the entity types. One complication is how do we specify these entity types of the arguments? Well, we can use a predefined ontology, or we can import a list of words. But in many cases, this is going to be a new class which we can't easily find. We'll take the simple view that the class is defined by a set of words. So we're just considering unambiguous terms at the moment. Users are not likely to do a good job assembling such a list. If I come to you and say, give me a list of 100 occupations, and I won't let you have coffee till you've given me 100. Probably going to be very thirsty before you're finished. But if I give you a list of 200 possible occupations and ask you to select 100, you'll probably do that in a few minutes. So we're going to take this general approach. System builds a list, the user reviews. So how do we build a list for the user? Rather straightforward approach based on context. The system ranks the corpus vocabulary based on similarity to a seed set. So you give a few occupations, professor, builder, lawyer, and it finds a lot more with similar contexts. In particular, we'll use the dependency tree to provide the contexts. So for each word, we'll look at its subject, we'll look at its object. If it's a noun, we'll look at the verb which dominates it, and so forth. So all the relations in the dependency tree will provide the context for us. And then we'll build a vector for each word, which is the PMI, pointwise mutual information, between the word and its contexts. So get a large context vector, use cosine metric on the context vectors to determine similarity of terms, and give the highest ranking words based on this cosine measure. And then the user will review this list and produce a set for us. Okay, and in doing so, after we've checked a number of examples, we can have it re-rank based on what we've selected so far and recompute the ranking. To see how well this works, we took two examples, which I'll show you online, if I'm lucky, in a few minutes. Generating a list of drugs from a corpus of drug arrests and a list of drug enforcement agents. So in both cases, we provided two seeds. We did the bootstrapping I just described using context information. After every 20 candidates were reviewed, we re-ranked, showed the list again to the user, asked the user to mark another 20, and measured how well we did. So in terms of finding drug names by this process, each iteration represents 20 examples. So altogether we looked at 200 items. And we got a recall on the order of 60 to 70% after looking at 200 items out of a set of 100. So about 50% of the items we looked at were correct. So we can do this process basically going down a list of 200 items in 5-10 minutes. The two curves represent the simplest approach. We do one ranking and use that throughout. The green line represents re-ranking after every 20 and produces a somewhat faster learning process. Similar result for finding agent names. The benefit of the active learning procedure is somewhat larger here. A small note, for most technical domains, it's important not just to consider single tokens, but to consider multi-word phrases. So for example, in terms of drugs, the phrase controlled substance indicates a drug for which a special license is required. And it has very different distribution and meaning from the word substance by itself. So we rank all these adjective noun patterns along with the individual words and use them in the entity sets and relation patterns. One point I mentioned a few minutes ago in choosing the basic approach was to have a mixed initiative active learner. And here's one example where the initiative can go either way. If a user has knowledge of the domain, they can provide the seed terms directly. Just type them in, have the process work. If you get a new domain and you don't really know what the main classes are, you can build these seeds automatically. Basically do an unsupervised clustering. It runs a clustering procedure, it gathers the terms, it says, here's a pair of terms which might be a good seed. And then you can take that potential seed and say, that looks fine, let's build a cluster around it. Or you can change the seed in some way in order to more closely match your needs. So you can either grant the initiative to the system and just say yes or no, or take control yourself. Okay, so the relation model, as I said a few minutes ago, consists of the dependency path plus the types of the arguments. So how do we represent the dependency path? The simplest way is we just give the complete path as a specification. That's a fairly simple, transparent approach. But requiring exact match is going to give a high precision but low recall result. Because if there's some small variation between the path in the training and the path in the test, you won't get a match. You can do somewhat better. I think the mouse had too much to drink last night too. You can do somewhat better by chopping the dependency path up into fragments and then allowing for partial matches between the dependency path and the test item. And that allows for some recall precision trade-offs. You can get better recall, give up some precision. Going further along this direction, you can get a richer feature set. More features will be better performance, but it'll make for a less transparent system. If you finally get 20 or 30 features and you ask the user, is this a good example or not a good example, they will have very little intuition left as to why they're being asked this question. So it may produce better performance, but we may sacrifice the intuition of the user. And at some point, the user may no longer be willing to answer these questions because they don't really understand why they're being asked this. Okay, so we tried two basic approaches, one of which I'll show you in a demo in a minute. One is the bootstrapping approach. The user provides the seed patterns. The system proposes new patterns whose arguments overlap with the seeds. So for example, NYU and Fred from the example we had earlier. So you give a pattern, it finds a pair of arguments, it looks in the corpus for all the other paths which have the same pair of arguments. The user accepts or rejects the pattern. This is a fairly intuitive process. And as I'll show in the demo, instead of showing the user the dependency patterns, you can present the dependency patterns basically as English phrases, so the user doesn't have to be concerned with syntactic relationships. So that's basically the simplest approach. A higher performance but less intuitive approach involves code-testing. In code-testing, there are two models or two classifiers. There's a local model, which basically corresponds to the model we've imagined until now, just looks at the individual example. And a global model, which captures the distributional similarity, so looks at other examples involving the same argument pair. The user provides a seed to train both models, and then it looks for what it believes should be the most informative example, which is one where there's the greatest disagreement between the two classifiers. So we have two classifiers. One says, yes, for sure, this is a relation, and the other classifier says, no way, this is definitely not a relation. And you measure the KL divergence between the two classifiers, pick one which has a very high divergence, go ask the user, update the model with this label from the user, and repeat the process. So this can potentially handle models involving lots of features and give you substantially higher performance, but as I say, some sacrifice in terms of transparency of the system. One further possibility to improve performance a little bit more is to combine this co-testing, this competitive classifier situation, with bootstrapping. So if the two classifiers strenuously disagree, you ask the user. If the two classifiers strongly agree, you just update the model and go to the next instance. So to give you some idea of how well these learners perform, the x-axis is the number of iterations. So each iteration, we asked 5 examples from the user. For 5 examples, I had to say, this was an instance of the relation or this wasn't. If we picked 5 examples at random, it starts off, this is the F measure for the final classifier. It starts off learning rather quickly, but it sort of flattens out. And in order to get to 40 or 50, I probably have to go somewhere over here. The co-testing, the basic co-testing without the bootstrapping, does much better. That's the green line. And if we combine the co-testing and the bootstrapping, we get the red line, and we get fairly close to the supervised performance. Supervised performance on several thousand training examples after labeling just 150 examples. So it's a quite efficient learning procedure, and it might produce in a few hours, labeling 150 relation examples, an adequate system, ballpark 50-55% F measure. Okay, some related work. We're certainly not the only ones who have tried to develop a system like this. There have been several groups who have reported on extraction development environments. As I've mentioned several times in my talk, our own focus has been on providing tools for novices and on combining guidance and flexibility. So if you want to control the process, you can. If you don't want to control the process, you can let the system do so. Here are 2 examples of systems designed primarily for expert developers. Something BBN calls extreme extraction. As if we're going to put you on a rack and get the relations out of you one way or the other. And it uses several of the similar approaches to what I've described. Unsupervised clustering, active learning, bootstrapping with manual review. But notice the bootstrapping is combined with handwritten rules because we're assuming an expert developer who can write rules to fill in cases which are not being handled. LCC, the Language Computer Corporation, also has similar set of IE tools. At the other end of the spectrum, several groups have worked on tools for novices. IBM Research Almaden has been a big proponent of having users write rules themselves. So they sort of disagreed with us and said if we have a good development environment, the user can write basically regular expressions and do the whole task. So they provide various corpus analysis tools and a development environment. Probably most similar to what we've described here is the work being done at Technische Universität Berlin, something called PropMiner. For classes, they used a fixed inventory, but in terms of the pattern learning, there's a lot of similarity. They focus on matching the dependency analysis and also render things as English phrases. So let me give a demo. First, a little bit about what you should see if it works. I always give this preface in case we have a total meltdown in the next few minutes. Okay, so we've been working on something called ICE, Integrated Customization Environment. The overall flow is based on adding and analyzing a new corpus. The basic steps are finding the new salient terms in the corpus, growing entity sets from these terms, finding frequent patterns, then involving these sets of terms. From the frequent patterns, extracting lexicalized dependency paths, and then finally growing relations from these initial patterns. So the specific demo I'll show in a minute analyzes a small set of press releases from the US Drug Enforcement Agency. Every time they find somebody crossing the border with an illegal drug and they arrest them, they put out a press release saying, look what we captured today. Okay, that's the corpus we'll be working on. So we pretend we don't have a list of drugs. They presumably do, but for the purpose of the demonstration, let's assume we don't have a list of drugs in advance. So we're going to build an entity set for the drugs and then find the relationship person sold drugs and a number of ways of expressing that. For the first step, finding the salient terms, we'll be counting the frequencies in the new corpus and comparing those frequencies to a background corpus of Associated Press. So look at what words occurred much more often in the new corpus, ranked by relative frequency. Then we'll build the entity set for the common drugs, type in a few seeds, maybe ask you what illegal drugs are popular in Brno. Type them in. Then arrest everybody in the room, right? Anybody want to leave now? Okay. So we'll select some seeds, rank the other terms. We'll assess the terms in the ranked list, see how well you know drug names from non-drug names. Save the accepted terms as a new entity set. Then once we've labeled all the drugs and in principle several other entity sets, we'll tag the entities in the large corpus, parse the corpus with a dependency parser, collect the paths which connect the entities, rank these paths by frequency, and present the paths to users as sequences of words. Okay, so we're hiding the dependency analysis from the user as much as possible. Then to actually build relations, the user or we will provide a seed pattern. We'll retrieve all the patterns with the same arguments as the seed pattern. The user will assess these patterns and say, are they representatives of the same relationship we started with? And we'll save the set of patterns as a new relation type. Okay, everybody cross their fingers. Unless you want coffee 5 minutes early, in which case you uncross your fingers. Okay, so let's see what we can do here. Okay, so this is the ICE interface. I've been told by several people this is too busy a screen. We should split it up. And so we're in the process of doing that, so bear with me. Sorry, I need my script. Okay, so you enter in a small corpus. For example, this is a very small one just for show. Has 16 articles. Okay, so it's done a count of all the words and articles, and we can look at the terms which appeared more often in the new corpus than in the standard Associated Press background. So enforcement partners, oxycodone, common illegal drug, and you notice it's a mix of individual terms and multi-word terms. Marijuana, this is a reference not to the system, this is a reference to Customs Enforcement Agency. Okay, so we'll take a somewhat larger, this is the press releases from New York City. So let me do find terms again. Okay, this is still a small corpus. It's smaller than we'd actually use. About 450 documents. And these are the words which appear more often in the DEA corpus than in the background. Okay, so suppose now we want to build a set of drug names. So I put in a seed. Let's see, nouns. Give it a local name so it doesn't mix up with any of the other entity sets. And let's see, what did we see before? Oxycodone. And let's see, find some other high-frequency drug here. Here's methamphetamine.
Pervitin. Do you have pervitin?
What?
Pervitin. Pervitin.
Not in this.
It's a drug produced in the Czech Republic.
In Europe.
Oh.
Germans like it.
Uh,
As far as I know.
You don't do much.
well, these are just drugs seized in New York City, so I'm not familiar with that. At least I have to claim that I'm not familiar with that. Okay, so I put in some seeds. I think I spelled it correctly. And it computes the contexts, ranks every word by its context, and here we get a list from the corpus. And I can rate some of these. So drug law enforcement is not an example of a drug. Okay, so you classify some. After you've classified some, you can re-rank it. Recomputes the similarities, gets you a somewhat better list. You can continue marking. Okay, when you're happy with it, you can save it and leave this process. Okay, so we've built a set. Presumably we take a few more minutes, but you can see it doesn't take very long to build an entity set for drugs. Now we'll do the same to get a pattern for a particular relationship. Oh, the patterns already exist. I computed it. So here are the most common dependency patterns. Person thanks organization. These are press releases. So we thank the New York City Police Department for helping to arrest blah, 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 blah. Okay, person sell drugs is one of the most common. So we'll see what paraphrases for person sell drugs we can find. Oops, the screen is a little bit, there we go. Okay, these are the patterns found by similarity of arguments. Okay, so in addition to person sell drugs, which was the seed, person sell drugs paste. So person sells cocaine paste. So that's presumably okay. Person ordered drugs, that seems to be different from selling drugs. So I'll mark that as a no, although we can understand that distributionally it's likely to be very similar. Person uses, let's see. I can look at the individual examples here. Person used and possessed handguns and shotguns while selling crack cocaine. So I always have the option, when it shows a particular example, of going back to the corpus and seeing the full example. Person conspires to obtain drugs. That seems different from selling. Person delivers drugs. That seems okay. Conspires to distribute drugs. Very long example, but I think that's okay. So we mark a bunch of examples, and then we can iterate and get more examples if we have a large corpus. We save the ones which we've marked as yes. If we had a larger corpus, we might have 50 or 100 paraphrases. but then you'd miss your coffee. So I kept the examples short. So that's the basic idea of the demo. Let's see. So there's lots more for us to do, and I'm sure you can give me some suggestions during the coffee break. We're concerned with how general this tool is. It works just fine for the ACE-type relations, but if people have very different relations in mind, it may not work so well. So we need to try this on a quite wide variety of relations. We have to figure out how much linguistics should be built in. So certain number of paraphrases like active, passive, relative clause are built into the system. We're not sure how much we should add. We have to see then how well people do using the tool. So we need real hands-on experience with users, which probably means our graduate students. And the general goal is we want to see this as sort of a conversation between the system and the user, where the user has some relationship in mind and wants to express this to the system. And the system asks questions to refine that definition. And so from that general viewpoint, we want to get a more flexible interaction between the system and the user to define new relations. Thank you.
So we have some time for your questions, please. Yes?
Well, thank you for your most interesting presentation. It's one question concerning the multi-word expressions you mentioned earlier. You said that then we can very well find patterns like adjective plus noun.
Yeah.
It's involved. Have you thought about languages that have a strong compounding component? I mean, German, Greek, or where in that case we don't have to look into the syntax, perhaps. So are we happy that we located a compound having all that information, or would we need to, extract information existing in the compound?
Well, for German, at least, I think the task would be somewhat easier than the English. I think my guess is that we could limit ourselves to the explicitly marked compounds as being the technical terms. I can't really speak for most other languages, I'd say.
Okay. Yes, please.
I would like to ask you about your example of extracting in your demo there was a phase, one of the first phases when you extracted some terms, and all the terms were in lowercase, and one of the terms was in uppercase, is the contact. What makes it a term and why is it in uppercase? I mean, starting with uppercase letter.
We collect frequencies initially based on the appearances with upper and lower case, and contact, this is a press release, so just to understand why contact is in uppercase, the press release says, for further information, contact so-and-so. It's sort of fixed, frozen phrase. And that appears always capitalized. So it's sort of one of our crude aspects of the system is it tries generally to distinguish names from nouns based on whether they're mostly capitalized. And in this case, it's coming to the wrong conclusion.
Ask about the demo, whether the paraphrases mechanism uses passive active phrases as a paraphrasing. I mean, there were phrases like person does something, but whether the phrases like drugs were sold by some kind of this in the passive voice, I mean.
Okay, so we didn't say much about this, but basically when we do the dependency analysis, we also do a small amount of syntactic regularization. And specifically, we convert passives to actives and fill in the zeroed elements of relative clauses before we do the pattern matching.
I mean, in Russian, for example, there are few types of phrasing except passive and active voices. So it's might be extended for other languages with a free order of words or some kind of this maybe. It's like a suggestion for the demo.
Oh, okay. Do we have a volunteer to make this change?
Yes, of course. Yes, we do this all. Of course.
Somebody want to come to New York for a couple of weeks?
Okay, there was another question, so please.
Thank you. In the early slide, you had a curve of recall increasing with the number of iterations. Can you say how the precision evolved as well?
This is for the entity sets?
Yes, I think so.
Okay, so when we're doing the entity sets, the user is passing judgment on every term in the ranking. So from the user's point of view, we're maintaining 100% precision throughout this process. If you want to measure this as a semi-supervised learner, then we would say the precision is about 50% altogether, but that's not how we were viewing the process. We were viewing it as human reviewed and therefore 100% correct.
Okay, please. Next question, yes.
I would like to ask whether you work with anaphora resolution when identifying the relation patterns or the relation occurrences.
Okay, so the short answer is no. That's to say, when we're building the patterns, we don't use the patterns involving pronouns for learning the patterns to be extracted. When we're running the actual extraction process, once we've learned the patterns, stick the patterns into the system for running extraction, then we do use anaphora resolution to pull out new examples. But we choose not to do that during the training because the anaphora resolution is like 70% correct, and so it introduced too many errors into the learning process.
Okay, so we have time for one more question. No? If not, I would like to thank you for the interesting and insight into and recent results from the area of information extraction. Really stimulating. Thank you very much.
Thank you.